Hi, my name is Kevin Miller, and today I'll be explaining what a standalone PV system is. A standalone PV system is an independent, fully integrated power supply with primary function to operate all of the consumer's loads without being connected to the utility. The design of a standalone PV system involves a number of steps and possible iterations to select and size the individual components required for a functional system. This presentation covers the basics of sizing and design and demonstrates the process by use of several worksheets. There are four critical processes necessary to design a standalone PV system. The first step is the load analysis. In the load analysis, you determine the magnitude and duration of all your AC and DC electrical loads on an average daily basis. The second step is to do a critical design analysis in which you will find the critical design month. This month is the month with the highest load demand and the lowest insulation. The third step is battery sizing. In this step, you estimate the battery storage size based on desired autonomy period and the maximum and average daily allowable depth of discharge. And the fourth step is sizing your PV array. You want to make sure your PV array can supply power to the loads and charge your batteries during the critical design month. And now going back to the first step in sizing a standalone PV system, which is the load analysis. The load requirements determine the size and cost of the PV system, therefore the energy efficiency of your appliances is paramount. For this reason, steps should always be taken to improve the efficiency of your loads. This may involve several factors, including getting more efficient appliances or being more cognizant of your energy use, such as turning off the lights or eliminating phantom load. As shown on the screen, here is what a typical load analysis would look like. On the far left column are the loads, such as the lights, computer, the TV, the oven. And the next column is just the quantity of those appliances. So there's 5 lights and about 1 of everything else. The next column is the appliance's power rating in watts. The column after that is the operating time, so how often or how many hours you use that appliance in a day. And then on the last column is the energy consumption. So that's basically just the power rating multiplied by the time you use it. So if you have an appliance that's a power rating of 50 watts and you use it for 5 hours, you're going to be consuming 250 watt hours. So that's basically the gist of the load analysis. Near the bottom, it'll give you how much AC power you're using, how much DC energy you're consuming, and also once it goes through the inverter, there's going to be a loss of power from the DC loads. This number down here accounts for those power losses. And the weighted operating time is basically a number to show on average how long during the day your loads are on, because not all loads are a continuous power draw. The next step is the critical design analysis. The goal of this process is to find the critical design month, which is the month with the highest load requirement and lowest insulation. Ideally, you would find the critical design ratios from several different orientations. However, in this example, we're going to be limited to the pitch of the roof. So you can see that we did our load analysis on each month of the year. And the one that was shown on the last page was December's load analysis. So you can see the average daily consumption in this column. And in the next column, you'll see the insulation for our area, which is Sacramento. And here you can see the peak sun hours per day. So the month with the highest design ratio is going to be designated as the critical design month, which is usually a winter month. And in this case, it's December. Now that we know our energy consumption in our critical design month, we can start sizing our battery bank. Battery size is variable and is generally based on the desired autonomy period allowable depth of discharge, and the low temperature derate factor. Autonomy is the time a fully charged battery can supply energy to the load when there is no input from the PV array. This is a critical part in sizing your battery bank. If there's a string of cloudy days, your system still needs to meet the load demand despite receiving little irradiance. As you can see here, we have our energy consumption, which is about 6.8 kilowatt hours per day. Our system size, as far as the voltage goes, is going to be 48 volts, and our desired autonomy is 3 days. So, in order to meet that period of autonomy, we would be required to have a battery bank of approximately 426 amp hours. The maximum allowable depth of discharge is the limit of battery discharge or usable capacity, and established by the low voltage disconnect set point on the system's charge controller. For a deep cycle lead acid battery, approximately 80% maximum DOD is typically used. The max depths of discharge must also be limited for batteries operating in cold climates to protect the battery from freezing. So after taking the depth of discharge right here and the temperature derating factor, the actual battery bank rated capacity that we'll need for this system is about 591 amp hours. Now that we know the battery bank capacity needed for our system, we can start selecting specific batteries to meet those requirements. In this example, we'll be using 12-volt batteries with a rated capacity of 200 amp hours. This means we'll need 4 batteries in series to reach the 48 volts, and then 3 strings of those batteries in parallel to reach the capacity needed. This means our actual battery bank rated capacity is going to be 600 amp hours. The load fraction is the portion of load operating power coming from the battery bank over the course of a day. So for instance, if you were using a load in the middle of the night, the load fraction would be 1, and conversely, if you're using a load in the middle of the day, it would be 0 because the PV array is supplying the load the power it needs. The average daily depth of discharge is simply the product of the load fraction and the average daily energy consumed divided by the actual rated capacity of your battery bank multiplied by the voltage of your system. And in this case, our daily depth of discharge is about 18%. Now that we have our battery bank sized and ready to go, it's time to start sizing our array. The array must be sized to produce enough energy to meet the load requirements during the critical design month while accounting for normal system losses. This ensures that batteries will always be charged and system availability will be high throughout the year. The required array maximum power current is determined from the daily load requirement and insulation for the critical design month, along with the DC system voltage and estimated battery charging efficiency. The battery charging efficiency is usually about 85%. The result is seen right here as being 61.8 amps. The array maximum power current has to be adjusted upwards due to soiling. The soiling factor usually is because of, say, dirt or leaves or any kind of debris that falls on top of the module, preventing the sun from generating the current. The array maximum power voltage also has to be adjusted due to temperature. If the temperature rises, the voltage of the modules will drop. Now that we know what is needed for the array maximum power voltage and current, we can start selecting specific modules to meet those parameters. In this example, we're using modules that have a rated maximum power current of 8.3 amps and a module that's rated for the maximum power voltage of 30.1. and the wattage of those modules is 250. To meet the array requirements, we would have to put 2 modules in series, and then we'd have to have 8 strings of those series modules to get the current necessary. This is a total of 16 modules in our array, and the rated power would be 4 kilowatts. And there you have it, we're finished. Now you know how to size a standalone PV system. No more pesky utilities knocking at your door. Hopefully my video adequately described the processes necessary to size the standalone PV system. Thanks for watching.